Hello everyone, welcome to SJC content. This is Dr.L.JETHRUTH, EMELDA, Assistant Professor in Mathematics, St.Joseph College of Arts and Science, Autonomous, Cuddalore, Tamil Nadu. In this video lecture, I am going to explain certain graphs and its property from graph theory for second BSc Mathematics. So as we all know, what is graph? Graph is nothing but a pictorial representations using points and lines, right? So here we have already know the basic definitions of certain graph: subgraph, induced subgraph, maximal subgraph, spanning subgraph, complete graph, and so on. Here I am going to give a definition for degree of a vertex. The degree of a vertex of the graph G is nothing but the number of edges incident with V, and is denoted by d of V or degree of V. Here the minimum degree of G is called is denoted by del of G, and maximum degree of G is denoted by delta of G. Here we note that if there is no edge of G incident with the vertex V, then the degree of V is 0. Such vertex is known as isolated vertex. If only one edge of G is incident with the vertex V, means then the degree of V is 1. In such case, the vertex V is called pendant vertex, and the corresponding edge is known as pendant edge. The next is, if there is a loop, then the degree of a vertex is twice, that is 2. It is counted twice. The next one is, a vertex of odd degree is called odd vertex. Similarly, the even degree is called even vertex. I have given one example here based on the degree. So here this is the figure taken, figure 1.1. In this figure there are 5 vertices. I have defined the degree of each vertex of the graph. Degree of V1 is 2. There are 2 edges incident with vertex, therefore degree of V1 is 2. And degree of V2 is 3. And degree of V3 is 1. Whereas degree of V4 is also 3. And degree of V5 is 3. Here V5, the degree of V5 is 3, right? So since the degree of V3 is 1, therefore it is called a pendant vertex, and degree of V5 is 5 because there is a loop, it is counted twice. Here we can note that the minimum degree of G is 1 and the maximum degree of G is 3. Here V2, V3, V4 and V5 are called odd vertices, and V1 is called even vertex because the degree is even. So the vertex V1 is called even vertex, where all other vertices are having odd values, odd degree values, therefore they are called odd vertices. Now we'll move on to the fundamental theorem, or we call it as a first fundamental theorem on graph theory, or Euler's theorem. It based on the degree of a vertex. Therefore, suppose the statement is like this: suppose G is a V, E graph, any graph, the sum of degree of vertices of G is twice the number of edges. That is, sigma d of V equal to 2 times of number of edges of the set, the graph G. So we shall see the proof now. Suppose G is a V, E graph, that is G is an order pair V, E. You may take any simple connected graph with the vertex set V and edge set E. Consider the edge E. It is already we know it is the ordered pair U, V of G. The edge E is incident with both end vertex U and V. Hence the contribution of E to the each degree of U and V is 1, and therefore the total contribution of each edge E to sum of the degree of the vertices of G is always 2 times of edges of G. That is, the degree of the sum of all degrees of Vi is equal to twice the number of edges. So this theorem, you can call it as a Euler's theorem. From Euler's theorem, we have sum of the degrees of each vertex of G is always even. This result is for every graph. The number of vertices of odd degree in a graph is also even. Suppose a graph has only odd degree vertices, means then sum of all odd degree vertices is also even. The next we'll move on to regular graph. A graph G is equal to V, E is said to be regular graph if all its vertices have same degree, that is the minimum degree and maximum degree are same, then the graph is said to be regular graph. A graph G is called k-regular graph if degree of V is k for all V belongs to V and k is non-negative integer. From this I have listed some notes. For a k-regular graph G, the minimum degree as well as the maximum degree are equal. That is, small del of G and delta of G is equal to k. Next is a 3 regular graph is called a cubic graph or trivalent graph. Next, every null graph is a 0 regular graph. See, these are some examples I have given. The first one is called cubic graph. Each vertex of degree, that is the vertex of the degree of each vertex of the graph is 3 here. That's why it is called as 3 regular graph or cubic graph. This is degree of V1. There are 3 edges incident with the vertex V1 everywhere here. So the degree is 3. D of V1, D of V2, D of V3, D of V4 equal to 3. The next is a Peterson graph. Peterson graph. So it has 10 vertices and 15 edges. 10 vertices and 15 edges. Here also you can see that the degree of each vertex of the graph having degree 3. Therefore, this is also one of the example for 3 regular graph. 3 regular graph. Now we have the degree of each vertex of the graph is 3, so it is also called cubic graph. Since small del of G, and that is del of G and delta of G equal to 3, so it is also known as 3 regular graph. Now we move on to the complete graph. A complete graph. A graph is said to be complete if every pair of vertices are adjacent. Every pair of vertices are adjacent. Okay. So it is also denoted by k. A complete graph on n vertices is denoted by kn, where n is any positive integers. These are some example for complete graph. The first one is k1 graph because it has only one vertex. The next is a k2 graph. It is a complete graph on 2 vertices. The third one is a k3 graph. It is a complete graph on 3 vertices. It is also known as triangular graph. The next is k4 graph, a complete graph on 4 vertices. The last one is k5 graph. It is a complete graph on 5 vertices. So in a complete graph, each vertex of V of G is adjacent to all other vertices, and so degree of V is always n minus 1 if every V belongs to V of kn. That is, if there is a kn graph, then the degree of each vertex of the graph is always n minus 1. And therefore, by definition of a regular graph, you can say that a complete graph on n vertices is called as n minus 1 regular graph, and it has n into n minus 1 by 2 edges. The next is every complete graph is a regular graph, but a regular graph need not be complete. Need not be complete. Now move on to the complement of a graph. Complement of a graph. Suppose G is a simple graph. The complement of a graph is denoted by G bar or G dash. It is also a simple graph with the same number of vertices, but if U and V are adjacent in G, means then they will not be adjacent in G bar. Okay, if the condition is satisfied, then the graph is said to be complement of G. So this is an example for complement graph. So this is a graph G. Here V1, V2 are adjacent, V2, V3 are adjacent, V3, V4 are adjacent, V1 and V4 are adjacent here. The complement of G is G bar, in which I have taken all the vertices V1, V2, V3 which are in G, but the edges which are in G are not in G bar. That is, if any two vertices are adjacent, definitely they will not be adjacent in G bar. Okay, right. So here using the complement graph, I have listed some properties. In a complete graph, every pair of vertices are adjacent, so its complement graph will be a null graph. So the complete graph, the complement of a complete graph will be a null graph. Suppose Kn is a complete graph on n vertices, then the complement of Kn will be a null graph consisting of n isolated vertices. It is also known as totally disconnected graph. So this is an example for complete graph and its complement graph. So this is a complete graph K4 graph. Then this is a complete graph K5 graph, and this is where complement of a K4 graph, complete graph, and this is also complement of K5 graph. So this K4, that is a complement of K4 as well as complement of K5 are isolated, or called totally disconnected graph whose degree is always 0. The next concept is isomorphic graph. So here let us take two graphs G1 and G2. They are said to be isomorphic, means if it is possible to define a mapping F from V1 to V2 such that if F satisfies the following conditions. One is F must be 1 1 and F is on to, the next will be, the last will be, if the order pair U comma V belongs to E of G1, if and only if F of U and F of V belongs to E of G2. Then the graphs G1 and G2 are called isomorphic graph, otherwise it is called non-isomorphic graph. If these three conditions are satisfied, definitely two graphs are said to be isomorphic. So this is an example for isomorphic graph. This is graph G1 and this is graph G2, where in graph G1 the number of vertices is 5 and number of vertices in G2 is 5. Similarly, number of edges in G1 is 8 and number of edges in G2 is also 8. Both have same number of vertices and edges, also same degree sequences. It possesses same degree sequences. So we say that there is a one-to-one mapping between them. So here V1 is equal to U1 to U5, V2 is equal to V1 to V5. If I define a matrix, mapping F from V1 to V2, such that F of U1 equal to V1, F of U2 is V2, F of U3 is V3, F of U4 equal to V4, and F of U5 equal to V5. So moreover, F satisfy 1 1 on two conditions, and if Ui and Vj are adjacent in G1, then F of Ui and F of Vj also adjacent in G2 for every I equal to 1 to 5 as well as j equal to 1 to 5. So these conditions are satisfied, therefore we can say that G1 and G2 are isomorphic graph. So thank you students.